Hello. Thank you for joining us today for the discussion of analytical investigations of plastics and polymers. My name is Dr. Adrienne Hoagland, and I have been working in the field of polymers for over 20 years. We will talk today about polymer selection, failures, and deformulations. Let's get started. Today we will talk about how to select the correct polymer or plastic for your application. We will then discuss some causes of polymeric failure, how they're investigated, and actually look at a real-life failure. Then we will discuss polymer deformulation and how they can help you prevent and troubleshoot issues. When consumers and manufacturers see and hear the word recall, as is shown here on your screen, it can bring a large amount of concern to the forefront. It can cost a company a large amount of money to resolve the issue. On the flip side, it can also cause a loss of confidence from the consumer in the manufacturer. Recently, in the news, there have been stories of various recalls, some involving polymers. Selecting the right polymer for the right application becomes critical to prevent these and other issues that can occur. When selecting your polymers, there are many questions to ask. On the screen are just a few. The first one is, what is the end use of the product? Is it food, beverage, medical devices, automotive, aerospace, building, etc.? What is the product going to be used for at the end? What physical form do you need the samples to be in for your application, both at the start of manufacturing and at end use, whether for the consumer or another supplier? Things like liquid. Does it need to be a liquid so it can flow? Does it need to be a solid so that it can be molded? Should it be in a suspension? Other application. What is the desired physical property that you need the material to have? Is there a certain color, such as an additive or a pigment that needs to be added? Is there a specific odor? In other words, reduction of odor. Or does it need to have a fruity smell? Should it be a foam? Does it need to be flexible? Or is there some other kind of property that you're looking at? How are you going to form your product? For example, open mold, closed mold, blow molding, extrusion, etc. What processing environments, once you have identified what type of molding, what types of environments are you exposing it to? Are you going to be doing extreme heat, extreme cold, wet, dry, anything else in the middle? Are there any environmental concerns? Today we're seeing the stories about plastic in the ocean. It's all over the news. We see all the pictures. A number of the large chain restaurants are looking at paper as alternative to plastic straws. And one just recently published that they're moving paper to paper straws in Europe. Do you need to have a biodegradable plastic so that the straws can be reused? Plastic straws can be reused, or some other recycling concern? Do you require a secure supply chain? For various industries, this is critical. You need to know where your material came from and how it was processed. This becomes important, for example, in the medical device industry, where the application is being used on human models. How much are you going to pay for what you want? In other words, what is the cost of the material? How much are you willing to pay for the plastic or the polymer that you're wanting? And based on what you pay, your manufacturing expenses, your distribution costs, and advertising, is this going to be profitable to you and your company? And as you can see, and more, there are more questions that you need to ask based on your specific industry and your specific need. Once you have decided on your supplier and have answered all of your questions, you will then want to perform a general survey of the raw materials to ensure that they are indeed suitable for your application. In this survey, you will want to do several things. The most common are listed here on the slide. First, you will want to perform a polymer characterization. This is important because do you have the right one? Do you have the right polymer? For example, what if you were sent polystyrene, but you thought you received polypropylene? You will also want to do a lot-to-lot comparison of the materials for consistency. This is a great practice to implement in one's testing environment. Not only will you have the confidence of the material, but you're also going to have confidence in the performance from the lots. You will want to perform a technical data sheet verification. This allows you to make certain that anything listed on the technical data sheet is in fact due to that specific product. Over the years of looking at many raw materials, I have seen situations where the wrong product is sent with the wrong technical data sheet. So this is a good time to make sure that you do have what the manufacturer says you have. You also want to take a look at total volatiles. Those are your low and high boilers, solvents, and such. Inorganic materials, that's clays, silicas, etc., and also your total percent water. What if you're told your material will have 5% solids and you find out it has 0.5% solids? How will that impact your process and end product? You also want to look at the total volatile organic content identification. VOCs are components that are emitted as gases from certain solids and liquids. They include a variety of chemicals, some of which may have short and or long-term adverse health effects. You need to consider, is your product going to be used in a situation that VOCs, no matter the amount, is unacceptable, or are they going to be in an environment where VOCs are okay for use and are acceptable? And finally, here on the list, an elemental profile to look at the identification of the inorganic compounds. Not just the amount, but this is the actual identification. For example, let's say you are a toy manufacturer and your resin shows up, you make your toy, and it goes out to children. Children are putting the toy in their mouth, and what if you later discover that the toy, that your base resin for your toy had lead in it? This would lead to the dreaded word of recall and other situations, financial, etc. The listing above are just some of the considerations when selecting your polymer. Now that we have discussed several considerations in selecting your polymer, let's discuss a failure that EAG Laboratories examined. This one is really interesting as it shows how the correct choice of polymer is important depending on the environment that it's going into. As can be seen from the slide on your screen, the problem that the client was experiencing was that as their employees were working in a shop area, light bulbs from a fluorescent fixture were falling out and onto them. This is obviously unacceptable to the client and to the manufacturer of the material, and both sides needed a solution. An initial approach was taken between EAG and the client to discuss the issue and then formulate a testing plan. However, let's first take a look at the failure before getting into the actual analysis. On your screen, you see a picture of 3 what are known as tombstones in the fluorescent lighting industry. On the left, you have an unused unit, or what we call controlled. In the middle and in the right, you see 2 used units, or what we're considering the failed units. You will notice with the black arrows that cracks have been pointed out where some of the failure occurred. These are also considered crazing in the longitudinal direction or crazing in the direction of the plane of the failure. This image on your screen shows a closer view of the longitudinal crazing. It starts at the top of the device and moves towards the bottom of the unit. As you can imagine, a crack of this size does impact the performance of the unit. Now that we have taken a look at the units and the failure, let's discuss the analysis plan and the subsequent results. The analytical approach that has been decided on has been displayed on your screen. It was decided that a comparative analysis between the failed and the controlled sample was to be performed. One of the tests that involved the failure was an inspection of the failures using optical microscopy. It took the failed and the controlled sample and were looked at in comparison. The next was to identify the base polymer. In this situation, proton NMR and horizontal attenuated total reflectance FTIR were used. For this, it was identified, the base polymer was identified in order to make certain that what the client thought they were buying was indeed the correct polymer. This takes us back to the selection slides where we were discussing it's important to make sure you know what polymer you have and that you didn't order polypropylene and polystyrene showed up. In this instance, they did indeed have the correct polymer and what they thought they had ordered. The thermal properties using differential scanning calorimetry and thermogravimetric analysis were examined for both the failed and the controlled samples. The thermal properties helped in further identification of the base polymer and the respective thermal profiles given off by the materials. Because the polymer had been correctly identified in the previous step, the thermal profiles could be looked up and compared to what was obtained experimentally. The thermal properties did match up to the composition of the base polymer. Molecular weight using gel permeation chromatography was examined. Having an incorrect molecular weight will impact the performance property of a material. In this instance, the molecular weight was confirmed and the values were shown to be equivalent between the failed sample and the controlled sample. Pyrolysis gas chromatography mass spectrometry was run to look for contaminants. In this instance, in the failed sample, a contaminant was identified that was not seen in the control. An additional benefit of the pyrolysis gas chromatography mass spectrometer in this application is that pyro can also help further confirm the base polymer identification. And in this, it did further confirm what had been identified by NMR and FTIR. So given what was detected in the failed sample, both the control and the failed sample were extracted, and the extraction was analyzed using gas chromatography mass spectrometry. In the extraction of the failed material, a chemical was identified as being present that was not seen in the controlled sample. Let's take a look at what was found. When the extraction from the failed sample was injected on the GCMS and the results examined using the NIST library that EAG has, we identified a compound known as dicyclohexylamine, or DCH. The match that came from the NIST library can be seen here in the insert on the right side of your screen. A 1.6 ppm standard was then prepared. The amount prepared isn't significant at this point because we did not do a quantitation. Rather, we made up a standard in order to identify the main peaks of DCH and confirm that that's what we saw. The DCH standard yielded a great match to the chemical in the failed sample. However, it's important for me to point out that had this been a quantitation, a minimum of 5 points on a calibration curve would have been made up and run, spikes would have been made and confirmed, and controls would have been made up and confirmed. So a much more rigorous process would have taken place if this had needed to be a quantitation. Upon identifying the polymer and the possible contaminant, several polymer modes of failure were discussed with the client. Let's discuss those. To briefly step back several slides, I mentioned the polymer had been identified using NMR, FTIR, HATR, and pyrolysis GC mass spec. As you can see from the slide in front of you, the polymer was identified as polycarbonate, which is a common amorphous thermoplastic. In other words, it's easy to form and it's excellent for injection molding applications. Amorphous thermoplastics are known to bond extremely well with adhesives and various solvents. Upon the identification of the polymer, the polycarbonate, along with the various testing that was performed, NMR, DSE, TGA, GPC, and such, possible failure routes were discussed with the client. These routes are shown on your screen. So some possible failure routes. Mechanical or design issue. Was there a repetitive motion situation? Was there something wrong with the design? Environmental stress cracking. This is a common problem with polycarbonates because they are excellent for many applications and are easy to form. The causes can be related to production or environmental. So during the production, were somehow cracks introduced and just not caught during the inspection? Polymer degradation. Many polymer chemists know that you can degrade a polymer with temperature, too hot, too cold, UV exposure, or chemical exposure, as we see in this instance. After all of our examinations, it was recommended to the client that EAG replicate the possible failure environment. Let's take a look at some images. In the slide on your screen, you can see the degradation study that was performed. On the left is a control, and then the three middle and the far right are samples that were exposed to the dicyclohexylamine, or DCH. You can see they were exposed at 23, 35, 53, and 65 degrees C. Every unit that was exposed to the DCH, regardless of the temperature and the days, failed. The unit that was exposed to the highest temperature did not fail, so we knew that it was not a temperature situation, but it was indeed the chemical situation. So what was the outcome of this failure investigation? So the outcome of this study was that the data suggested that dicyclohexylamine, or DCH, was indeed responsible for the degradation of the polycarbonate via a reaction that happens between amines and polycarbonates, known as aminolysis. Through an examination of the cutting fluid at the material, DCH was identified as a corrosion inhibitor present in these fluids. The client used this information to select a different type of cutting fluid in their facility. However, the client could have also chosen to go the route of selecting a different polymer base for their tombstones. This goes back to our selection slide. End-use application. Are you selecting the correct polymer for your application? How's it going to hold up under various environments, such as, in this instance, a corrosion inhibitor being used in a cutting fluid? So there's applications that we look back to the selection, and you can see at this point how these kinds of selections go back to help prevent a failure analysis. So next is polymer deformulation. The question one might ask is, how does a polymer deformulation help you to prevent and troubleshoot issues? Well, this is just one of the many areas where EAG Laboratories excels and where we work with our clients to work on these kinds of issues. In this example today, we're going to discuss a deformulation of a pressure-sensitive adhesive. Let's dig into it a little bit. The background for this project was that a beauty product supplier wanted to develop their own pressure-sensitive adhesive for wigs. This pressure-sensitive adhesive was to stick to the scalp and then to the wig and hold the wig in place so it did not move. They liked the performance of an existing pressure-sensitive adhesive that medical applications were utilizing. They wanted to be able to make this adhesive and possibly patent the system for their application. So EAG's objective in this project was to identify the components that were present and then quantitate what had been found in this adhesive in the attempt to generate a comparable product. For a deformulation, you need to have initial observations. In this situation, the initial observations take us back to the polymer selection section that we discussed earlier on. And just a couple of the initial observations are here, or questions that you should be asking. What is the end use of the product? We've already discussed that. What do you want the product to do? What state do you need the product to be in? Liquid, solid, suspension, foam, etc. Color, odor, and in this instance I put use caution. You want to make sure that if your product has an odor, that the odor is acceptable for the application. Foam, flexible, what do you need this material to do? So again, we go back to that polymer selection, and once you've made your selection, a general survey needs to be performed. For this particular deformulation, I've included a couple of steps of the general survey that were performed. This is certainly not an exhaustive list, but it shows some of the tests that were done. Loss on drying to determine the amount of volatiles in the material. We evaporated the adhesive. What was left? Loss on ashing to determine inorganic content. We ashed the material to see what inorganic components were still there, how much inorganic material. We investigated solubility. And in this situation, solubility is important. If it's a wig adhesive, you don't want your adhesive to be water soluble. Think about it. You're out in a pretty good rainstorm. You don't want your wig to be shooting off your head. Carl Fisher, how much water is in your adhesive? Water in an adhesive for an application like this, you need to know how much is actually there. Gas chromatography mass spectrometry. We did a VOC. What were the VOCs? What was off-gassing? Was there anything coming off that could potentially have short-term or long-term adverse health effects? We did FTIR and proton NMR to look at the non-volatile component identification or identify the base resin. And then EDXA was run for this. You could also do ICP-OES or ICP-MS. EDXA, or Energy Dispersive X-ray Spectroscopy, can take a look at the elemental profile of your material. So depending on the concentration, what you're looking for, there's several different techniques that you could run in this situation. So the next couple of slides contain just a few of the test results and the tests performed. Let's take a look at those. As can be seen on your screen here, the GCMS identified several different solvents as being present in this adhesive, one being ethyl acetate and one being isopropanol. The next steps that were taken was polymer identification. Again, we previously discussed this in the selection and also in the failure. Identify the polymer that is there. Make sure you know what you have. So for this, I'm just going to briefly discuss FTIR, pyrolysis GCMS, and NMR. In the slide on your screen, you can see the FTIR analysis of the dried residue of the pressure-sensitive adhesive. In this situation, the material had to be dried down because isopropanol and ethyl acetate were detected in the material. The best match spectra, which is an acrylic polymer, was identified in the bottom spectrum. In this, we were able to confirm that the base of the material is most likely some form of an acrylic polymer. In this instance, some of these acrylic polymers can help to improve the flow and leveling when it comes to the pressure-sensitive adhesive. The pressure-sensitive adhesive was then analyzed using pyrolysis GC mass spec to identify the portions of the backbone and additionally help identify any other potential monomers or additives in the system. As can be seen from the chromatogram, there are a lot of peaks. These peaks are based on fractions of how the material broke apart or if there's additives or anything else in the system. During a deformulation that is performed, every peak is examined and best matches are applied. This aids in the identification of the various polymers in the system. So as you can see, just a few peaks have been identified for this example, as shown to your left, around about 2 and 4 minutes. As can be seen, the acrylate portions are broken back down into their individual units, telling the scientist who is working on this that there were at least 3 portions to the polymer backbone. Those were identified by X, the Y, and the Z repeat units. And as a side note of interest, the Z repeat unit is what was identified by FTIR. The sample was analyzed as received using proton NMR. As can be seen from the spectrum on your screen, the solvent peaks from the ethyl acetate and the isopropanol are overlapping the sample peaks. This creates a problem when trying to do any kind of interpretation or identify the number of repeat units. So the solvent had to be extracted. Let's take a brief look at how the solvent was extracted from the system. As I mentioned, the solvent peaks are interfering with the NMR, so a solvent exchange needed to be performed. Additionally, by using NMR, we needed to determine the relative amounts of monomers in the backbone to aid in helping the client either resynthesize or formulate the product or create one with similar properties. However, a really interesting phenomenon of this particular material that was identified was that the material cross-linked once the solvent was removed. To prevent this, a solvent exchange method was developed and performed. The sample was repeatedly dissolved in something like toluene or chloroform. so that the polymer was isolated, but not fully removing it from the solvent environment. We also had to make certain to keep the solvent to polymer ratio as close to the original formulation as possible to also prevent cross-linking of the material. Once this was done, and the solvents that were selected were chosen so they would not be an interfering solvent when looking at the NMR was reanalyzed. In the spectrum in front of you, you can clearly see that the interfering solvent was indeed removed with our solvent extraction process. This allowed a much clearer picture of the sample peaks. Based on the structure identified by pyrolysis GCMS, we were able to further identify and quantitate the amount of the acrylate polymer present. That is seen by the fact that X became 75, Y became 20, and Z became 5. All these techniques were pulled together and yielded this information. I won't, however, be covering the entire set of testing that was done on this project today. That could take us the better part of an hour or two to discuss. However, these are some of the many tests that are performed during a polymer deformulation, or as some of you know them, reverse engineering process. Conclusions and future work for this deformulation include the pressure-sensitive adhesive was found to be a cross-linked acrylic system. The 3 tests that we previously discussed showed that to be true. A procedure for synthesizing acrylic polymers for pressure-sensitive adhesives was identified through an investigation of the patent literature. The synthesis group at EAG Laboratories performed a first pass at generating the system. The formulated product was tacky and of a lower viscosity. I would like to point out that we worked with the client to make certain that they did not violate any existing patents. The client then took the material and performed trial studies and is considering their options to move forward. So you come back and you say, so how does a deformulation help me? Well, we go back to end use, starting materials, those kinds of things. If these can be identified, you can identify, are you getting the right components, the right materials, the right polymers for your application? What are you looking for? What are you aiming for in your materials? What do you want to know? Deformulations can also help you identify what's in the competitor's material, but can also help you identify how hard it will be for the competitor to deformulate your material. Let's recap. It was shown at the beginning of this presentation, selecting the right polymer is critical to your application and bottom line, not only for performance, but also the trust and confidence of the consumer. When a polymer is utilized in an environment that it is not favorable to, as we saw with the tombstones on the fluorescent lights, failures can occur. If the right material is not selected, again, a failure can create an issue. And finally, when in doubt about the system you are looking at, or you want to make certain all the components you ordered are there, a deformulation or reverse engineering can aid you in the prevention of these issues. There are many steps in the life of a polymer, starting from raw materials through finished materials. How can EAG help you? We are an independent third-party testing lab, and we can provide unbiased results. We can do your raw material examination. We can examine your technical data sheet. We can look at finished product examinations. We can do trade secret investigations. Has somebody violated what your product is? Or, in the case of some situations, as I previously mentioned, we can deformulate your own product to see how hard it will be to get the trade secrets. Competitive product investigations, as I mentioned, we can look at your competitors' products. Failure investigations. As you saw with the tombstones and the lights, we can look at the failure and help you identify what caused it. Litigation support. EAG is fantastic at working in a legal environment, so if somebody violates your trade secrets or a failure happens, EAG can also work with a legal team in supporting you in that way as well.